Ever stop and think about what holds everything together? And I mean literally everything. The water in your glass, the phone in your hand, even the air you're breathing, it's all held together by this invisible glue. We call it chemical bonding. So yeah, let's dive in and see how this whole thing works.
So that brings us to the big question, right? Why do atoms even bother sticking together? I mean, in nature, you almost never find an atom just hanging out by itself. They're super social. But why? Why not just fly solo? Well, funny enough, to figure that out, we've got to look at the very few that do.
All right, Section 1. To understand why most atoms are so desperate to pair up, we're going to start with the total exceptions to the rule. You could call them the ultimate introverts of the periodic table.
Okay, so say hello to the noble gases. We're talking about elements like helium, neon. These guys are perfectly content all by themselves. And the reason is simple. Their outer electron shell, it's completely full, packed. This makes them unbelievably stable. Think of it like a perfectly balanced Jenga tower. It's not going anywhere. They don't need to interact with anyone. They've basically reached a state of chemical zen.
And this right here, this is the absolute key to understanding everything we're talking about today. There's this fundamental rule in nature. Every system wants to be more stable. So chemical bonding, it's not some random thing that happens. Nope, it's nature's way of lowering energy and reaching that same amazing stability the noble gases already have. It's like the ultimate goal for almost every atom.
Okay, so if stability is the name of the game, what are the rules? How do all these other atoms get to that super chill noble gas state? Well, that's where something called the octet rule comes into play.
And the octet rule is actually pretty simple. The whole idea is that atoms will do pretty much whatever it takes, give an electron away, steal one, share one, all to end up with 8 electrons in their outermost shell. 8, that's the magic number. It's that full, stable shell we keep talking about, the one the noble gases are born with.
Now, to keep track of this whole electron game, chemists came up with a really simple tool. They're called Lewis symbols, or you'll hear them called dot structures. It's easy. Each dot stands for one of those super important outer electrons, the valence electrons. It's basically a scorecard, tracking each atom's progress on its quest to get to 8.
All right, so the goal is 8 electrons. How do they get there? Turns out there are 2 main strategies, 2 main ways they can pull this off. Let's break down these 2 paths to chemical happiness.
So the 2 big strategies are called ionic and covalent bonding. Ionic is like a total giveaway. One atom just straight up gives an electron to another. Done. Covalent, on the other hand, is more like a partnership. 2 atoms decide to share electrons. They create a little community pool. So you've got a giveaway versus a partnership. 2 totally different ways to get to the exact same goal, that stable octet for everybody.
Let's take a look at a classic ionic bond, table salt, NaCl. So you've got sodium, and it has just one lonely electron in its outer shell. It is dying to get rid of it. Then you have chlorine, which has 7. It's so close to a perfect 8. So it's a perfect match. Sodium just hands over its electron to chlorine, boom. Now, when they do this, they become ions, which is just a fancy word for an atom with a charge. Sodium is positive, chlorine is negative, and you know what they say, opposites attract. That attraction locks them together in a super strong ionic bond. And the best part? Both atoms are now totally stable and happy.
But okay, what happens when nobody wants to give up an electron? Let's say you have 2 chlorine atoms. Each one has 7 outer electrons. The solution here isn't a giveaway, it's a partnership. They each contribute 1 electron to a shared pool in the middle. By sharing that pair, now both atoms get to pretend they have 8 electrons in their outer shell. Nobody actually loses anything, but everybody wins. It's a perfect example of covalent sharing.
Okay, so these dot structures are great for keeping score, right? But they're kind of lying to us. They're hiding a massive piece of the story because molecules aren't flat little drawings. They're real 3D objects. And it turns out their shape is absolutely everything.
Just look at water, H2O. If you draw its dot structure, it looks like a straight line, right? HOH. Looks simple. But here's the crazy part. If water was actually shaped like a straight line, life on this planet, well, it probably wouldn't exist. The real story is way, way cooler.
So the reality is, water isn't straight at all. It's bent. And the reason why? It's fascinating. If you look at that central oxygen atom, you'll see 2 pairs of electrons just hanging out, not bonding with anything. We call these lone pairs. And these lone pairs are bullies. They take up a ton of space, and they literally push the two hydrogen atoms down and away from them, forcing the whole molecule into this bent shape.
And this whole idea is wrapped up in something called VSEPR theory. Now that's a mouthful. It stands for valence shell electron pair repulsion. But really, it's just a fancy way of saying something super simple. Electrons hate each other. They're all negatively charged, so they push each other away. Whether they're in a bond or a lone pair, they're going to arrange themselves in 3D space to get as far away from each other as physically possible. That's it. And get this, there's even a pecking order to this pushing and shoving. The biggest, strongest repulsion, that's between two of those lone pair bullies. The weakest repulsion is between two pairs of electrons that are already tied up in bonds, and the lone pair versus bond pair is somewhere in between. What this really means is that those lone pairs have the most say in what the final shape of the molecule is going to be. And this is where it gets really cool, because VSEPR isn't just an explanation, it's a predictive tool. It's like a recipe. You just count up the bonding pairs and the lone pairs around the central atom, and you can figure out the molecule's exact 3D shape. So, 4 bonding pairs, 0 lone pairs, like in methane, you get a perfect tetrahedron shape. 3 bonding pairs and 1 lone pair, like in ammonia, you get a pyramid. And 2 of each, like in our friend water, you get that super important bent shape. Every time.
Okay, so who cares, right? Why does it matter if a molecule is bent or straight or shaped like a pyramid? Well, it matters because a molecule's shape is its destiny. Shape determines function. And that simple fact has some of the biggest real-world consequences you can imagine.
Take a look at this number, 104.5 degrees. That isn't just some random angle. That is the exact angle inside a water molecule. And it's a direct result of VSPR theory at work. It's the perfect, precise angle that you get when those 2 lone pairs and 2 bonding pairs push each other away as much as they possibly can.
And here is why that bent shape is the whole ballgame. See, oxygen is a little greedy. It pulls on those shared electrons a bit harder than hydrogen does, so the electrons hang out closer to the oxygen. Now combine that with the bent shape, and what do you get? You get a molecule with 2 distinct sides. The oxygen side is a little bit negative, and the hydrogen side is a little bit positive. It creates what we call a polar molecule. It's basically a tiny, tiny magnet.
And being a tiny magnet, that's water's superpower. It's the whole reason we call it the universal solvent. Think about it. When you drop salt, our old friend NaCl, into water, those little water magnets get to work. The positive hydrogen side of water grabs onto the negative chloride ion. The negative oxygen side grabs the positive sodium ion. And together, they just rip that salt crystal apart. This one ability, the ability to dissolve stuff, is fundamental to, well, pretty much all life on Earth.
So, let's wrap this up. We started with a really simple idea, right? Electrons push each other away. And where did that lead us? To the very property of water that makes life on this planet possible. It really makes you think, if these basic rules of repulsion can build something as essential as a water molecule, what else in our world is being built, right now, from the ground up, by these same fundamental forces?